So outages are inevitable, but we should design our architecture such that if a component is down, it should not lead to a complete outage. A partial outage affecting few services is fine, but a complete outage is catastrophic. It is easy to say this, but really hard to implement. In this video, we dissect yet another GitHub outage, gather few interesting insights about that microservices architecture, spend some time discussing and understanding the importance of having a smaller blast radius, and talk about a foolproof way of achieving that. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue. Instead, a small focused group of 50-60 engineers every cohort will be brainstorming systems and designing it together. This way, we build a solid system and learn from each other's experiences. The course to date is enrolled by 600 plus engineers spanning 9 cohorts and 10 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The coolest part about the course is the depth we go into and the breadth we cover. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale for any advertisement business. In all, we would cover roughly 28 questions and the detailed curriculum split week by week can be found on the course page, which is linked in the description down below. So if you are looking to learn system design from the first principles, you will love this course. I have two offerings for you. The first one is the live cohort based course which you see on the left side, and the second one is the recorded course which you can see on the right side. The live cohort based course happens every 2 months and it will go on for 8 weeks. While the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would highly recommend you going for the recorded one. Otherwise, the live cohort is where you can participate and discuss things live with me and the entire cohort and amplify your learnings. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass, and I would highly recommend you to check that out. I put the link of the course in the description down below. So if you are interested to learn system design, go for it. Check out the link in the description down below, and I hope to see you in my next cohort. Thanks. So like always, we start with the incident report and here it goes. So what it says on January 28, 4 a.m. UTC, our service monitors detected abnormal levels of errors affecting action service. By the way, most of the outages that I've seen of GitHub are related to action service. My best guess is because it is very high throughput service, it is very prone for outages. A lot of them have been around action service. But yeah, some abnormal level of errors affecting action service. This incident resulted in the failure or delay of some queued jobs for a period of time. So as you all know, action service of GitHub is primarily powering the GitHub actions, in which like whenever a commit happens, you have to trigger a workflow and all of that happens. So a lot of jobs are asynchronous. So because of this incident, there was a failure or a delay of some queued job for a period of time. That's fine. Jobs that were queued during the incident were ran successfully after the issue was resolved. This is a very important point to note. So here, even though their service was down, when it got back up, everything like the job that were queued, they were put to a completion. And this is a very important point around designing an architecture. So if this was not asynchronous, so here we can clearly see that this was an asynchronous workflow where most of the things were done asynchronously. So your queue was acting as a buffer, right? Or your message broker was acting as a buffer. And if that was not there, then if this was modeled in a synchronous way, the right field is right field and the data is lost. Right? So that is where whenever we are designing most of the architecture, think about can we do it asynchronous way, because that would give you fault tolerance out of the box. Okay, so what happened? We identified that the issue was caused by an infrastructure error in our SQL database layer. Again, something to do with database, the most brittle component in every single architecture out there, but that's fine. Okay. The database failure impacted one of the core microservices that facilitates authentication and communication between action microservices. So this gives us a very nice sneak peek of their architecture. So what it says is something happened on one microservice, part of its actions microservice that handled authentication and communication. So this tells us two very interesting things. The first interesting thing that it tells us is that GitHub Actions, although most of the folks would model it as a singleton microservice that powers GitHub Actions, but internally GitHub Actions itself consists of multiple microservices. One of them that we saw in the previous outage was around GitHub Actions Premium Service Runner, something around that, right? So there is not one microservice powering GitHub Actions. There are multiple components that power GitHub Actions altogether, and they all share a database. Either they share a database, because see, the outage happened because there was an infrastructure error in the SQL database layer, right? Which means that either all of the actions microservices shared that common database and were directly dependent on it, or indirectly dependent on it through synchronous way. So somehow every single one of this was linked to this one database, and if that was affected, it would affect every single service out there. And shared database is a speculation. They have not specified it, but it's a very common practice. Although people think that, hey, we should not have shared database, we should have a database for every microservice, but it is infeasible with respect to cost. If you do not have shared database, a lot of network latency would shoot up and you would incur a lot of cost. In most cases, that is not needed. So sharing a database looks like an anti-pattern, and it is indeed, but a lot of people adopt it. Right? And there is nothing wrong with it so long as if outage in one does not let your entire infrastructure go down. Right? So this is a very common way to do it, and looks like GitHub, if not all services were sharing a database, but at least through synchronous dependency. So either directly dependent on the database or indirectly through a synchronous dependency were dependent on this database. The second key point that we talk about, that the service that got affected handled authentication, right? And why you think services or microservices would need authentication? Like, they're all part of your infrastructure. Why would they need to have authentication in place? So this authentication is not for end user. This is microservice to microservices based authentication. Like, why? So most companies, when they design architecture, it's always zero trust architecture, which means even if two services talk to each other, they would not trust. Like, imagine you having a notification service. It is not having any authentication of its own. Imagine some random service gone rogue or an engineer gone rogue in a different team and started invoking APIs of this notification service, which started sending messages to your end users. Very poor experience, right? So that is where, in most cases, the way microservices are designed, they're designed with zero trust, right? With zero trust, they ensure that even when a service wants to communicate to any other service, it needs to be authenticated and authorized to do that. And the service that got affected in this particular outage was the one that handled communication. So communication is typically shared communication and authentication. Obviously, they would not reveal the details. It's all speculation, but you get the gist, right? It handled authentication and communication. Okay, so what next? We know that the outage happened on the database layer, but we also know that, let's say if a database master is down, a replica is auto-promoted. A replica is promoted to be the master. So then this really should not have been an outage, because in most cases, automatic failovers are configured, right? So that's exactly what GitHub said. In normal circumstances, automated processes would detect that the database was unhealthy and failover with minimal or no customer impact, because this is a very regular exercise where master goes down and a replica is promoted to be a master. Hardly few writes fail in the span of half a second or a second, but nothing major happens. It's a very standard operating procedure. But this was a normal circumstance where this should have happened, but it did not. Okay, but before we jump into why it did not, let's spend some time on how it happens. So database failover is very common to happen. So you have a master node, you have a replica, master goes down and replica becomes a master. But how? It is not some magical thing that happens that automatically replica will be promoted. So there is typically an orchestrator setting who is monitoring when the master is down. So there has to be someone who is monitoring if my database becomes unhealthy so that he can promote other node to become the master. Who is doing that? That is orchestrator. But how would orchestrator do it? It would rely on some metrics. It would rely on some telemetry. It would rely on some data that would tell it, ki, hey, master is down. Let me promote a replica to be the new master. Someone has to do it. It is not magical ki it would automatically happen. But as we know, this did not happen. So this did not happen. What it says, in this case, the failure pattern was not recognized by the automated processes, and telemetry did not show any issues with the database, resulting in a longer time to determine the root cause and complete mitigation efforts. So there is a classic case where your database is down, but your telemetry is not showing it, and this is very common. Not very common, but this is common. This is indeed common, where the automation that you may have written might not be capable of detecting this failure because it might be trained on some particular patterns, but not on this pattern. And it might be very possible that the entire database is not down. Only a fragment of it is down, or some particular kind of tables are logged, or not everything, or it is not a very obvious outage on the database, right? So this is very common, right? So here the orchestrator was not able to identify that the master was down. So failover did not happen. Because failover did not happen, and because the telemetry also did not show that the database was having an impact, and very common this kind of thing. Because it could not show ki something's wrong into the database. How would engineer even come to know that a database is down, right? So it required them longer time to determine the root cause, because up until the time they would reach to the database, hey, is there a problem with the database or not? A lot of steps needs to be validated or to ensure that, hey, downtime is not because of this. Because the first thing when an outage happens, people look at telemetry. When they look at telemetry, they say, hey, their database is doing fine, let me debug at other place. But that did not happen. The database was down, but the telemetry was not showing it. Right? Okay, so this happened. So what did they do? It took time for them to determine the root cause. So what's the next step? They did not specify it in the incident report, but there would be two possible ways to do it, right? But there are one very elaborated way also, but two very common way to do it. First of all, do a manual failover. You know that the master is down, manually promote a replica to be the new master and reconfigure your database. Very easy, hardly takes 15-20 seconds to do it. Most cases, that is just a script that you need to run and would do the failover. Case number one. Case number two is reboot the machine. So if you know that the master is down due to a transient failure, reboot the machine. During that reboot, writes would fail, but in any case it is failing because there is an outage. So that's fine. After few minutes, everything would be back up and normal, right? But in case you'd want to dive deeper into other ways of doing it, I've discussed a few more approaches in other dissection videos. I would highly recommend you to check that out. Right. So that's what GitHub also talked about. The telemetry did not show any issue, and the database resulted in the longer time on determine the root cause. It took longer time for them to do that. Okay. To help avoid this class of failures in the future, we are updating the automation process in a SQL database layer to improve error detection and failover. Everyone says this, and this is something which becomes a step 0 after the issue is mitigated, to ensure that you do not see the outage because of the same reason again. And that is a very important thing to do anytime when you face an outage, right? So that would be the first thing. So as part of their long-term strategy to ensure that the outage doesn't happen for the same reason, they would need to do is understand this failure better, right? First of all, they have to detect the failure, because this time database was down, but they were not able to figure it out. So they need better failure detection. Second, they need better automated failover, where when they proactively know that database is down, very quickly they should be able to failover. So going through or re-auditing the scripts, re-auditing the automation is very important to ensure that if similar thing happens in the future, it does not take a relatively longer time to debug it. It should be pretty quick. Okay. Furthermore, we are continuing. This is a very important point. Furthermore, we are continuing to invest in localizing failures to minimize the scope of impact resulting from infrastructure errors. This is an important point. So here we saw how impact on one database caused entire GitHub's actions to be affected, right? Because that critical database handled authentication communication, so synchronous dependency, direct or indirect, everything got affected, right? And this is what tells us importance of localizing failures. So failures are bound to happen, but we all should be thinking about how can we ensure that our failures are localized. When I say localized, it implies that if a particular microservice is experiencing a failure, or let's say a database experienced a failure, only that microservice should be affected. Everything else should not go down. There should be default values to handle. There should be a default response code that you are throwing out, or just absorbing the failures, or something around that. Depending on the use case that you have, you should be designing your architecture such that whenever something goes down, it just affects the bare minimum infrastructure components or your microservice components whatsoever. And this is very important. It's really, to be honest, it's easy to say, but it's very use case specific on what you are building, how you are building, what your organization's engineering maturity is, and then you would be able to employ the corresponding architectural pattern so that your failures are localized. But this is basically called as blast radius. So when you have an outage and if something breaks, the things that are affected by it is the blast radius. It's like when a bomb blasts, what all things are affected. So how big is the blast radius, right? Is it 5 kilometers, 10 kilometers, 15 kilometers, right? So similar to that, whenever an outage happens, let's say a database went down, what is the blast radius? So when a component goes down, how many components it takes with it? So this is what we have to keep it at bare minimum, right? So when you keep the blast radius at the bare minimum, so not a lot of services get affected. So you would see an outage, but it would be a very partial outage where only one service is getting affected. But how do you do this? A very good way to do this is to have asynchronous dependency. So blast radius, a very typical way to look at this is blast radius is larger when the dependency is synchronous, and it is smaller when the dependency is asynchronous. So try to model the communication between your services asynchronously, as in use message brokers, message streams like SQS, Kafka, RabbitMQ to do the communication between microservices. Do it synchronously only where it is like extremely essential, right? Things that can be done in an asynchronous way, try to model it to do it in an asynchronous way. Keep them loosely coupled, right? And it totally depends on your use case. There is no golden way or there is no silver bullet to this. It is very dependent on your use case, how you are modeling it, but this should be your thing that you do on day zero, right? If you are going for a microservices arc, always think, are these services loosely coupled? Am I burdening a single service with a lot of synchronous requests, or am I giving a lot of responsibility to this one service? Can I break it down into multiple smaller services such that if one of them goes down, I would have a smaller blast radius? And also, what if when you are communicating to any service, think about what if that service is down? How are you gracefully handling the failure on this service? Right? Very important to think about whenever you are doing it. But in most cases, if you think about this one point, can I do this communication in an asynchronous way, would automatically make it loosely coupled, right? So think about this. Whenever modeling any architecture, modeling any inter-service communication, think about, can I glue them with a message broker or a message stream? That's it. If you start with this is a very good starting point. If you start with this, you would automatically start to design loosely coupled microservices, which inherently would have a very small blast radius. And when it has a smaller blast radius, you would always see partial outages, not mega outages like this. And yeah, that's it for this video. This is what I'd want to convey, the importance of having loose coupling and to ensure that you have blast radius, or basically your failures are localized. They don't propagate across the system, right? Very, very, very important when you design microservices based architecture. I'm really glad that GitHub wrote about it. GitHub wrote about it. They are so open about their outages because it helps us learn. It helps us learn on importance of these small practices that most people just basically take it for granted unnecessarily. Don't do that. It's really important. Okay, amazing. That's it for this video. If you guys like this video, give this video a thumbs up. If folks like this channel, give this channel a sub. I post 3 in-depth engineering videos every week, and I'll see you in the next one. Thanks a ton.